will put PhD here. And the title is Tuning the Period of Square Wave Oscillators by 2D wave.
Hello everybody, thanks for being here. In this talk, I will present work where we explore the possibility to tune the period of a square wave with two different delays. This work has been done with my PhD advisor, Numerical, and in collaboration with Professor Thomas Darnay. This is the outline. First of all, there is an introductory part where I will include some basic concepts, derived systems, and what is a square wave. This is a kind of pulsating dynamics. And I will present different derived systems where we can have square wave dynamics, and in particular in opto-electronic oscillators, because these are the units of our dynamical model. Then I will explain in detail our model, and after that I will explain you the instabilities of the steady state of the system, and how through the linear stability analysis we can derive the period of the square wave solutions through the Hopf equations. After that, I will derive nonlinear maps to determine the amplitude of the solutions, not only for the primary square wave solution, but also for the secondary implications. And to continue, I will show you some numerical simulations of the full dynamical model. And finally, I will show you what is the effect of a small mismatch in the delay times on the synchronized solutions and the form of the square wave. And finally, I will summarize the results. So let's begin. We study in this work delayed systems, each one with an intrinsic delay, and they are coupled also with delay. We focus on periodic solutions, and in particular in synchronized solutions. And we study how robust are these solutions under parameter mismatch. Time delays in physical, biological, or chemical systems are a source of oscillatory instabilities. In optical and opto-electronic systems with feedback, usually the time delay is much larger than the intrinsic time scale of the system. And this large delay can be useful for applications. An interesting regime that characterized with large delayed feedback is square wave switching. But what is a square wave? First of all, a square wave is characterized by plateaus and fast transition layers between the plateaus. So it is a kind of pulsating dynamics. Here we have an example. And what can be useful for? The generation of such pulsating dynamics has been studied in the past few years, not only for its fundamental interests, but also motivated by applications such as optical clocks or other binary logical applications, the generation of stable microwave signals, or optical sensing. Square wave switching has been studied in edge-emitting lasers subject to polarization-rotated optical feedback. We have in the external cavity of a laser two modes, but from the two modes, the transverse electric and the transverse magnetic, because they have different gains, there is only a natural supported mode, and this is the electric one, the transverse electric. The transverse magnetic is not supported normally by the laser cavity. But with polarization-rotated optical feedback, one can rotate the polarization state of the feedback in such a way that the transverse electric mode is coupled to the transverse magnetic mode. To do this, one normally uses a Faraday rotator, which is a device that rotates the polarization of the light 45 degrees. Then, in this way, we have 45 rotation, then the light is reflected by this mirror, and in this way there is another 45 rotation, and at the end there is a 90 degrees rotation. And this part is to detect the intensity in each of the polarization directions. Here we can see the detected intensities. We can see that they are square wave, there are plateaus, and between the plateaus, fast transition layers. In this case, they are in antiphase, and the period is related to the delay. In particular, it is close to twice the delay time. Square wave switching has also been studied in mutually coupled edge-emitter lasers. Here, in this setup, the transverse electric mode of each laser is rotated and coupled to the transverse magnetic mode of the other laser. And in this case, one has again square waves, but they are strongly asymmetric. The duty cycle can be controlled by the injection current or the feedback strength. Using this setup of polarization rotated optical feedback, square wave switching has also been studied in other systems as vertical cavity surface emitter lasers or ring lasers. A different scheme that can give rise to square wave switching is an electronic oscillator. This device has an optical part and an electronic circuit. Light from a laser diode is split into two beams with a magenta interferometer, and at the end there is a fiber delay line of time delay TG, and the light is detected by this photodiode, amplified, and used to modulate one of the branches of the magenta. Then the dynamical variable is proportional to the applied voltage, the voltage applied to the modulator. And as a result of this voltage, one of the arms suffers from an straight phase modulation with respect to the other arm. As a result of this, there is a nonlinear interference between the two branches, and then the dynamical equations have this coordinate. This is the dynamical equation has this square in the cosinus. This is the cosinus square. This is a delay integral differential equation. We can see that if there are three different time scales, then this is a stiff problem. First of all, we have the delay in nanoseconds, which is between the two characteristic times of the filter, the lower time in picoseconds and the larger time in microseconds. This means that to solve this problem, we need to take a small integration step in order to cover the fast dynamics, but also to integrate during a long interval of time in order to cover the slower dynamics. This integral term can be eliminated using this new variable, and then one has a system of two delayed differential equations. Usually, one in these kinds of problems rescale the time to the delay time and introduce other adimensional variables, particular y, and these adimensional parameters, and then one has this system. This system has a steady state solution given like this. And this is an example of a square wave obtained for a positive value of the feedback phase, this parameter. This parameter fixes the operating point of the modulator. And here we can see that again we have plateaus and fast transition layer between the plateaus. This is the stationary state, this line, and for values of the feedback strength less than 1, this is equals 0, the only stable solution. When one increases parameter for beta larger than 1, square waves emerge, and this variable has a triangular shape because it is the integral of the square wave. For this system, one can obtain an amplitude equation if one relates the value of fits at consecutive plateaus. Onto this, and this map can be obtained in the limit epsilon going to 0, this parameter, and delta going to 0. With these opto-electronic oscillators and positive feedback, one has solutions will have period twice the delay time. There is a correction to the period which is due to the time needed for the fast transition value between the plateaus. These solutions emerge with Hopf bifurcation. For low values of the feedback strength, lower than 1, consider the steady solution, and for larger values, here we have that the solutions are sinusoidal. And if one increases the feedback strength, the solutions become more and more squared. This is not the only type of solutions. For the feedback, for negative feedback, that is for a negative value of the feedback phase, one has these solutions will have a period once the delay time. And these solutions are quite different from the other one because they are asymmetric. You can see that here, changing the feedback phase, one has different solutions with different duty cycles. And you can control the duty cycle with the feedback phase. This, again, is a correction to the period which is of the order of epsilon, because epsilon is related to the lower characteristic time of the filter. This is not the only solution with a negative value of the feedback phase. There are other slower solutions. We have a period close to the higher characteristic time of the filter, theta, that is in microseconds.
When you talk about negative phase, you mean negative time?
No, negative values of the feedback phase. The phase in this equation, this parameter.
The parameter that controls.
Yes.
Okay, the phase there. Okay.
Depending on this parameter, you can have solutions of period once the delay or twice the delay. The possibility of controlling the period of the square wave was analyzed in the past. We studied by Ikeda and co-workers, and this is the Ikeda differential equation. It was introduced by Ikeda in the 80s to study the instabilities of an optical bistable resonator. And we thought this was very important because with this, Kensuke Ikeda was able to demonstrate that chaos also exists in optical systems. Ikeda and co-workers demonstrated that multiple solutions with frequencies that are multiples of a basic frequency appear through successive Hopf replications. Here we have the different domains where these solutions appear. And these solutions, as one increase the parameter mu, which is here the feedback strength, have a road to chaos. That is this transition occurs via period downwind, but it is different on each branch. On the fundamental branch, there is only one solution for a particular value of the feedback strength. However, on the higher harmonic branches, there are multiple solutions. These solutions, different solutions that one encounters, not increasing mu, but increasing these, are called isomers and can be found changing the other parameter is 0. This parameter here. This is an example with the third harmonic. Here n stands for the order of the harmonic and m for the order of the instability. This isomer can bifurcate to this one or to this one. And this one can bifurcate to 4 different isomers, and this one to 2 different isomers. And as a result, there are 6 isomers of period 8. These are only 2 examples of them. IFISC and co-workers then realized that such a system could be used to encode information in high-capacity memory devices. To codify the isomers for the harmonic of order n, one divides the time interval into n domains. For instance, this is a harmonic, the 7th harmonic, then one has seven domains, then they are repeated. They can change the thing, but they are repeated. And one needs 2 to the minus 1 symbols for each domain to represent these isomers. This is an example. This was demonstrated with several experiments using an electro-optical device, and it was found that higher order harmonics were very sensitive to noise. But one could use also an external modulation to impose the desired period. And doing this, these harmonics were stable. We have seen different systems, different delayed systems that can give rise to square wave dynamics. Now, in this work, we use 2 mutually coupled opto-electronic oscillators to generate square wave switching. Each oscillator operates on its own delayed feedback, and the presence of the 2 delays allows a large number of solutions, square wave solutions, larger than with 1 delay. We will analyze the bifurcation mechanisms using asymptotic techniques, which will be valid in the limit of large delays. And we expect that our results could be generalized to other delayed nonlinear systems and lead to similar results. So, well, why we have chosen this kind of systems? First of all, because they exhibit a rich variety of dynamical regimes with different potential applications. They can be used as chaos generators for safer-based communication, also to generate microwave periodic oscillations with high spectral purity, for instance, for applications like radar. And also, they have been recently implemented in experimental demonstration of a photonic liquid state machine, which performs a kind of neuromorphic computing. This is known as reservoir computing. And because of their advantages also. In particular, they are insensitive to optical phase variations, and they can be electrically driven. Let's continue with the dynamical model. We have 2 mutually coupled opto-electronic oscillators. Light from a laser diode is split into two beams, and each beam fits a Mach-Zehnder interferometer and an electro-optical loop. A fraction of light goes through the self-feedback loop, and takes a time t if to reach the self Mach-Zehnder interferometer. And another fraction of light goes from one loop to the other loop and takes a time tc. These are the feedback strengths. At the end of the self and the cross feedbacks are combined and are detected by a photodiode. The signal then is amplified. This is an electric signal, here represented in black. And this electric signal is used to modulate one of the branches of the Mach-Zehnder interferometer. Again, we have here a nonlinearity due to the difference between these 2 branches for the 2 systems. And this system is more complex because the 2 loops are coupled. The dynamic.
You assume that the self-feedback delay time and the connection between the two layers, the two devices, is also the same. Is this because it's just for simplicity, or is because for some application this is needed? When you have only
we
one.
consider for simplicity only two different delays, and we aim to control the period by these two different delays. So there is the delay, the self-feedback delay. Yes, the two systems have the same feedback delay, and the coupling delay are also the same. Yes, for simplicity. And to try to understand something first. The dynamical variable is proportional to the applied voltage to the modulator, like in the single equator oscillator, and this is again the offset phase that fits the operating point. Then the dynamics. There is something that I haven't said, that it is that the dynamics results from a combination from the nonlinear interference between the two beams here due to the Mach-Zehnder and a linear filtering process that is associated to the electronic circuit. So we have no linear, in this equation, the dynamics is given by 4 delay differential equations, 2 for each system. There is a linear part, a coupling integral part, and then this is a self-feedback term, this is a coupling feedback term, and this is an interference term. For simplicity, we take identical systems. In particular, the characteristic times are the same. Here, sorry, this parameter is a laser power. And this one, this is the difference of phase between these two different branches of these two different modulators. But for simplicity, because we consider that the systems are identical, also in this case is equal to 0. The feedback strengths are also considered identical, and the feedback delays as well.
Question. Don't you have the condition that gamma 11 plus gamma 12 equal 1? Because you are splitting the total intensity in 2. So somehow that's...
Yes, this is normally condition, but as we consider that all the feedback strengths are the same, this is automatically satisfied. Here.
Well, but I mean, you don't have 4 independent coupling strengths, you have only 2 independent coupling strengths. Because the other 2 fulfill gamma 11 plus gamma 12 equal to 1. Yeah, because you have to split the other 2.
In principle, it is true that in the splitter you split the divide in 2. But then when you detect it photodiode and you go to an amplifier, then you have different amplification in principle in the two systems.
Okay.
And then you could compensate for that. So at the very end, you end up having still 4, in principle, 4 effective independent coupling constants. You could have 4, okay? You have 2 coming out of the splitter and 2 coming from the 2 gates. Okay. But for simplicity here, we consider everything to be an equal amplification to avoid.
This system has a steady-state solution, 0 for the x of its oscillator, and y is given by this. This is a constant. Here one can define, as for the single oscillator, I-dimensional variables. Also, it is useful to define this new variable subtracting its stationary value, in order to have that this variable is also 0 as it is. And we rescale all the variables with TC. We define is 0 as the ratio between the delay. This is an important parameter in the rest of the talk. And these are dimensional parameters, epsilon and delta. And then we obtain these dimensional-based equations. Taking into account the time scales of the system, TC, the coupling delay, in nanoseconds, tens of nanoseconds, and the characteristic times in macro and picoseconds, then these parameters are very small. In particular, epsilon is very small. Epsilon is multiplying this term, so it is responsible for the fast transition layers between the plateaus. But we will ignore it in the analytical calculations. What we cannot ignore in general is this term delta. Why? Because it is responsible for the zero time average of the variable is in the stationary regime. This is the only possible solution which is compatible with the condition of non-divergence of this equation, because X is coupled to Y. Let's continue. Because of the large delays of the system in comparing to the other temporal parameters, square waves are the dominant solutions. Here, remember that the times are scaled with Tc and the E0 is related to the two delays. In this work, we always consider values of E0 in the interval 0, 2. So they are quite larger than the other time scales. And now we will address the following question. What is the dependence of the period on the ratio between the two delays? To answer this question, we determine the Hopf bifurcations of the steady state. To first approximation, we consider delta 0. And with the same, we cannot do this, but yes. We can do this in this case because the zero solution satisfies the condition of time average 0 automatically. So as a first approximation for the linear stability analysis of the steady state, we can do this. Then we consider small perturbations around the steady state, and we formulate the linearized equations for the perturbations. Here we have that Chi is an effective bifurcation parameter, as we will see later, and it is proportional to the laser power and the pickup strength, and it also depends on the phase. The linearized equations have exponential solutions. At lambda equals 0, we have the Hopf bifurcation. For lambda negative, the perturbations decay, and for lambda positive, they grow. If we take the limit of large delays, which is given by epsilon going to 0, we obtain an homogeneous system for C1 and C2. And from the condition of non-trivial solution of this system, that is that the determinant is 0, we obtain this characteristic equation. Thus, there are two families of Hopf bifurcation. First, considering the positive sign, we have, if we substitute this here, that C1 is equal to C2, thus this corresponds to a family of Hopf bifurcations that led to in-phase solutions. From the real and imaginary part of this characteristic equation, we obtain these two equations. And from the first one, there are two possible cases, but only the first case leads to physical solutions if one takes into account the second equation. And then it follows that the frequencies are given by this, and that the bifurcation parameter is related to the frequency through this expression. Second, if we consider the negative sign, we obtain that C1 is equal to minus C2. Thus, this Hopf bifurcation corresponds to solutions that are out of phase. And from real and imaginary part of the characteristic equation, we obtain again two equations. And again, from the first one, we have two cases. And now, in this case, only the second case, sorry, because here we have to do this. Only the second case leads to physical solutions if one takes into account this second equation, and this cannot be possible. So if one takes this equation and substitute it, this equation is equivalent to this one for the frequencies, and taking into account the other equation, one obtains this expression for the bifurcation parameter related to the frequencies. Now, we consider that she is positive. We could consider that she is negative and do another analytical calculations, but for this work, we consider only she positive. This means that we are going to obtain only some results of the system. No, there are other solutions. And we plot the Hopf bifurcation curves as a function of this parameter is 0. What we see here is that all the curves exhibit a minima at chi equal 1. And from a physical point of view, this is interesting because this corresponds to the first bifurcation that one encounters, increasing chi, which is proportional to the greater power. And chi equal 1 corresponds to a not multiple of p for in-phase solutions and an even multiple for out-of-phase solutions. Taking into account the expressions obtained before, we can obtain expressions for the ratio between the delays. Here, for in-phase solution, we have obtained that the ratio is odd-odd, and for out-of-phase solution, it is odd-even. We can also obtain expressions for the period in terms of S0, that was the aim of this calculation. And now, if we plot the possible solutions, we see that not all the values of S0 are possible. This is one result. Also that there are multiple solutions coexisting for the same value of S0. And also that not all the values of L and M for the case of in-phase solutions and of K and M for the case of out-of-phase solutions are possible, but only some ones. For the fundamental solution, one needs to have the minimum values of L and M or K or M. And to obtain the higher harmonics, one has to multiply the numerator and the denominator by an odd number. You cannot multiply by an even number, but because you would obtain a ratio odd, which is not satisfying the expressions. Then we introduce a new number, G, that accounts for the order of the harmonic, and we relate this index M and L to the order of the harmonic and to the index of the fundamental solutions. If we do this, we obtain that the period of the harmonics is always a not multiple of the fundamental period. And this is also satisfied for the solution, of course. But the expressions in terms of E0 are different because, as we have said, the values of E0 are different for in or out-of-phase solutions. We have obtained an expression for the period.
I am lost. When you have a Hopf bifurcation, you calculate the frequency. This usually you determine the frequency of the small oscillations around the steady state. What is the rate? There is some magic so that this period of the oscillation is the same as the square wave oscillation, which is not a small, it's not a sinusoidal oscillation around the steady state.
Yes, at the beginning it is a sinusoidal oscillation.
Yeah, but why is the period the same for when you are close to the Hopf bifurcation and later?
Because the solution is more than the Hopf.
The oscillation is more than the Hopf, but then usually when you go far from the Hopf bifurcation, in general you can change the frequency. But in this case, it seems that it doesn't change.
It doesn't change with that. there is more correction we have, but in principle,
Yes.
the
You mean
figure
Yes,
that
the periods have
correction
more
is small
correction
because
with
epsilon is small.
epsilon.
In general, it will be large, but correction is small, it's a small correction.
yeah.
Yes, the correction becomes smaller as the period becomes larger. The correction to the period. Because the transition layers become wider. And in the case where epsilon goes to 0, you have the perfect square wave. And the period is given by twice the delay in the cases we have seen in the introduction. Okay, one can obtain a period for a solution, and now we also would like to have an expression for the amplitude. So to do this, we try to find nonlinear maps for the amplitude of the square wave solutions. This can be done in the limit of large delays if one consider in this case in-phase solutions, this conditional synchronization, the dynamical equations can be written in this form, and then taking into account the expressions for the ratio between the delays and the period of the oscillation, one can relate the period to the different delays. Is 0, remember that is the rate of the delays, and all times are scaled to Tc, so this is related to the self-feedback delay, and this one to the cross-feedback delay, 1. And if we introduce this here, we obtain these equations. But this is not the map still, but what we can do is to integrate this equation. Now, to do this integral, we consider that the variable is constant over half of the period. And we introduce this notation where each k is located at the beginning of the semi-period. If we do this, then these equations become these ones. And now, if we subtract this equation, the first one, evaluated at k minus 1, from the same equation evaluated at the next step, k, we obtain this equation. And combining this equation with this one obtains this map. This map, one can do the same thing for the out-of-phase solution. I'm not going to explain this, but you want later. It is the same. It is exactly the same, but we change this part. And we can do this, and what we obtain is exactly the same map. And this is important result. The map is independent of the nature of the solution. We obtain the same map for in and out-of-phase solutions. Now, we want to generalize this map to more general forms of synchronization. In particular, we consider this generalized black synchronization where each one and each two are lagged or synchronized with a lag time which is given by the difference between the two delays, scaled to Tc. If we consider this, then the dynamical equations can be written in this form. And also, if one considers that it is practically constant during a plateau of length St, and one requires this consistency relation and introducing this notation, in the limit of large delays, we can obtain these equations. And now we do the same thing than before. We take this equation and subtract the equation evaluated at two consecutive steps and combine the resulting equation with the second equation, we obtain a map which is valid for other solutions than in or out of phase periodic square wave solution. It is valid also for higher harmonics, periodic solutions, and for non-periodic solutions, because the only condition that we have imposed is that each one and each two are synchronized with a lag time. This is another thing that we can extract from this map is that there are multiple solutions that coexist for the same value of E0, the rate between the rates. And each one has different plateau lengths, P. Q is an integer. From this map, one can obtain the in-phase and out-of-phase square wave solutions that we have presented before. In particular, for primary in-phase square wave periodic solutions, the length of the plateau is given by the period divided by 2. And if one takes into account the expression that we have obtained before, we obtain that the ratio between the delays is a not multiple of the plateau length. And the same result applies for out-of-phase square wave periodic solution. In general, for a periodic solution with period twice the length of the plateau, we have this periodicity condition, which says only that the variable is repeated at each period, which is the thing. And we take this and the other things explained here. One result is that Q is equal to 1 for primary square wave solutions. That Q equal 1 does not imply that we have a primary square wave solution, but we know that if the solutions are primary, they have Q equal 1. And finally, the map obtained in this general form can be further simplified in the case of primary square wave solutions. If we consider that it's centered around 0 and that it changes the sign at each step. If we do this, the map can be written in this form. This is a sinus map. And now, let me show you the bifurcation diagram of this general map for different values of the feedback phase. We can see that for this particular value, the map is symmetric. For very low values of the bifurcation parameter, the only stable solution is equal 0. And we see that for G equal 1, this solution becomes unstable as predicted by the linear stability analysis. And the amplitude of the solutions that emerge then can be follows this sinus map in this interval. Also close to the bifurcation point, the amplitude grows as the square root of this parameter minus its critical value. However, for other values of phi, this map is not symmetric, but it has a symmetric part. And the point at which the square wave solutions become unstable depends on the feedback phase. Here, they are stable during they are stable for higher values of G. And here, we can see that at lower values, they are already unstable. This map predicts the instabilities of the square wave solutions and also other instabilities. Now, I will show you some numerical simulations of the full dynamical model. We have checked that the zero solution becomes unstable at G equal 1 by numerical simulation. And here, we can see that for very low values, but bigger than 1 has already square wave. Here, the plateaus are slightly tilted, and the tilting is an effect of delta. And this effect decreases as the amplitude increases. Here we have an example of in-phase solutions that can be obtained with a ratio odd-odd, and an example of out-of-phase solutions that are obtained for a ratio odd-even. And we can see that the amplitude is the same for in and out-of-phase solution. This can be also seen in this figure, where we have plotted with different symbols the amplitude of the solutions for different values of the ratios between the delays. And in solid line, the prediction of the map. And we can see that the numerical simulations are in agreement with the prediction of the map. As we have seen before, increasing chi or increasing p, the laser power, or gamma, the feedback strength, because chi is proportional to these two parameters, the primary square wave solutions become unstable, and higher order solutions emerge. Here we have the bifurcation diagram for the amplitude of the solutions as a function of the feedback phase. And here we can see that there is a central region where the solutions are square wave. Here we have an example with 0.18p of a square wave solution. But farther away from the center, there is a period doubling bifurcation. This is an example with phase 0.15. And here we can see that the two plateaus are not symmetrically centered around zero. And also these solutions are not lag synchronized, are just synchronized by lag. In fact, all the solutions are synchronized by lag, and in particular cases of lag synchronization. This is an example of the coexistence of multiple solutions for the same value of the ratio between the delays. Here we have on the left panels in-phase solutions, and on the right panels out-of-phase solutions for the same values of the delays. And J is the order of the harmonic. We can see that with this system we can reach up to the 20th harmonic. All the solutions are stable against numerical perturbations, and the fundamental solution is the one that has the highest margin of attraction. And then, starting from an arbitrary initial condition, one usually ends up in the fundamental solution. Nevertheless, one can select properly the initial condition in such a way that one can make the system to operate in any of these harmonics. Finally, we have analyzed what is the effect of a small mismatch in the time delay, in the delay times, on the form of the square wave. Here, what we have done is to fix one of the delays, in particular TC, to 90 nanoseconds, and to vary the other delay. We can see J, is the index of the harmonic. Here we have the fundamental solution, and here the first harmonic solution for different values of the set feedback time. We can see that for 30 nanoseconds we have a perfect matching condition, because zero is odd, and then the solutions are almost squared waves, and the periods are these ones. With a very small mismatch, the solution is still square wave, but the transition layers become wider. Increasing a bit more the mismatch, with a mismatch of the order of 2%, intermediate plateaus appear. And we can see that these plateaus are not centered symmetrically around zero. We can see that the plateau with positive hits is lower than the plateau with a negative value of hits. we can see also that the solution is degraded. But despite this degradation, the amplitude of the solution is maintained. These higher harmonics and the other more are more sensitive to the mismatch than the fundamental solution. As higher is the order of the harmonic, as sensitive to the mismatch is. But we can conclude that all these solutions are robust to mismatches of the order of a few percent, and that several solutions can coexist in the presence of a small mismatch in the delay terms. Finally, I will conclude. We have studied the synchronization conditions for in and out of phase periodic square wave solutions in a system with two delay coupled opto-electronic loops. We have shown that in and out of phase synchronization is possible if the ratio between the two delays satisfies a rational relationship. And synchronization is in phase if the ratio is odd-odd, and out of phase if it is odd-even. We have derived analytical expressions in the limit of large delays for the period and the amplitude of the square waves. We have obtained that the map for the amplitude is the same for in and out of phase solutions. We have also obtained a more general map valid for secondary square waves and other solutions. We have shown numerical simulations that confirm our analytical results. And we have seen that these periodic square waves are robust to mismatches in the delay times of the order of a few percent. Also, we have demonstrated the coexistence of many in or out of phase square wave solutions, periodic. And this provides a large degree of flexibility to tune the period without changing any parameter of the system. This can be interesting for applications such as information encoding. Finally, let's say that our methodology and results can be generalized to other systems of coupled nonlinear oscillators with multiple and different delays. That's all. Thanks for your time.
So that you can tune the period without changing parameters, but you have to change the delay times.
Yes.
I mean, you can have
But yes, you can change the delay times and you can have different periods, or as Terry said, you can have several harmonic coexisting for the same value of this zero. That's why I said that we have a large degree of flexibility, because we have the coexistence of many solutions for the same value of the ratio between the delays.
You mentioned the information coding encoding at the end, and you mentioned in the beginning of your talk in relation to the work of Davis and Ida on the isomer states. Do you find these isomer states also in this kind of system?
Yes.
You concentrate mostly on the
No.
stability.
Here, that's what I want. I have tried to just introduce you a bit. We have also analyzed the case of we have also found in numerical simulation that with G negative we have one periodic square wave solutions then, and they have different types of DG cycles.
But I was rather referring to the isomer states.
Yes, exactly.
Which are the higher harmonics with different modulation patterns on top.
if you go back a couple of transformations.
No, but here,
No.
the beginning.
No. Go one more. Just the previous one. This one. This one. Those are very
But
strong.
that's a period doubling. I wouldn't call it yet an isomer.
Well,
No,
then you want
but
to
changing the offset phase, you can find different solutions. and in particular changing not only the offset phase but also its sign. If you take negative values of the offset phase, you will obtain different solutions and also with different periods, and these are isomers because they can be found for the same values of the parameters of the laser power as in the case explained in the introduction, where we have the same feedback strength. Here also for the same feedback strength you can have different solutions. Then the parameter is 0, and here the parameter that we need to change is chi. The chi depends on the phase, and in particular it depends strongly on the sign of the phase.
Yo, can you speak again?